Can everyone see that? All right, sweet. Yeah, there's everything. Cool. So I want to talk to you about IPFS, or I like to call it the permanent web. This is a crazy idea. It's really cool. It's kind of out there, and I'm trying every single thing I can to make it work. And it's really valuable, and hopefully you'll agree with me after this conversation. So, all right. So today there's like some problems in the web, right? Like links break, which is really stupid. Like, why would a link break if a site goes down, right? Like, maybe we have the file. What if you're requesting some file from the server and I have the file? Why can't I just give you the file, right? If the server is down, or when something gets slashed on it, right? Or Hacker News or whatever the term is today. Why do servers go down when HTTP just like routes all this traffic into that server, right? We're serving tons of static traffic through HTTP, which is a protocol that directs everything to one point, a single point, right? And people try to compensate for this by creating large distributed systems underneath what appears to be one host, right? Because the URL points to where you can get that object. So people try to get away with this, right? But I think there's a better way. I think that it's time to think about the protocol of the web as not this thing where you fetch a specific file from a specific place, but rather where you fetch a specific file, period. And that anyone should be able to serve that file to you, if they can prove that's the right file, right? Like, that's the question. Like, how can you make sure that they're not serving you bogus stuff? It turns out that these things have been solved, right? Like, we know how to do these things. It's just that those ideas came after HTTP. Those ideas came around late 90s and the beginning of 2000, right? So I'm here to change your mind about how we should do the web and push for this, and also kick off like a plan to upgrade the web as it is today. All right, so IPFS, the permanent web. Mad science, right? Like, this is crazy. This is bold. Chances are it's not going to work, but all good ideas start as crazy, crazy projects. All right, so this is a website that doesn't exist yet. It'll be up soon, so you'll be able to find out more. And I'm going to give you some background. I'm going to give you an overview of how the protocol works. I'm going to give you some use cases, and we're going to talk about the future. So it all started really, really simply, right? Like, I wanted to build a dataset package manager. And this sounds like a simple thing. Like, I want the data around the world to get to my computer really easily. I just want to say, like, that data package manager install some data set. The problem is the data is really big, so you can't really host it in package registries the way that apt or anything else like that works. So you really want something like BitTorrent, right? And Git at the same time, right? Because if you take regular BitTorrent and you distribute some data set through it, and you then need to change it, now you have to create a new torrent, which is crazy, right? And BitTorrent has like this patch idea of making BitTorrent mutable, but it hasn't really been implemented. It's not widely deployed, and it really seems like bolting on another idea to a protocol, when in reality we should be thinking carefully how these protocols get interfaced to everything else. So that's what I'm here to tell you about. And then as I started working on this, suddenly I saw the light and everything was clear. It's kind of crazy, but IPFS is this content address versioned peer-to-peer file system. And content address just means that when you request an object, you request it by its value in a way. A really easy way to do that just means request files by their hash, right? So if I have the hash of a file, I can just tell anyone, hey, give me this file, I have the hash. And I can check, whenever you give me something, that I can hash it and see if it's the right value, right? That's pretty powerful. What if URLs work like that, right? And then we could do that upgrade to HTTP, where we could get to the point where anyone can serve anything, and the client can check it, right? You don't really need to get it from a specific person. The other part is version. So Git is awesome, right? You can get to version all your code really nicely. And what if your entire file system worked like that? What if, like, when you had a file in your computer, it was automatically versioned smartly? Git notoriously is known for not being really able to handle really large files. And I'm here to tell you that that's not Git's fault. The Git design is really good, and it can handle really large files. It's just that the tools haven't really been upgraded to do so, because Git's main point is to be a source code system, right? It's not really about data. So in reality, we just could upgrade the tools, or again, like make better tools for the next decade. So, and the latter part, okay, so it's peer-to-peer, meaning that anyone should be able to serve you something, and you can get it from anything, right? So peer-to-peer has this notion of, kind of like fringe systems, but in reality it just means I can talk to any server and get something back. HTTP is a little bit peer-to-peer, but it doesn't tend to be thought about that way because you don't think about running an HTTP server locally when you are requesting files, right? You have this client-server model. So let's just fuse those two and say an IPFS node can talk to any other IPFS node and get files. Cool. So the goal is to connect all of the devices with the same system of files. And this is kind of like the web, right? The web already did this, but I really think it needs to be as high performance as you can so that you can run the entire machine off of that system, right? Like what if the web was your root file system? That's kind of like where we want to get to. It's just that right now, if you thought about doing HTTP requests for every single file that you want to access, like that would be insane. Because you need to talk to specific servers, right? But what if we could do away with that? All right, so you can think of it as kind of Git plus BitTorrent in a way. The proper equation looks something like this, where it's like a DHT and BitTorrent and Git and this thing called SFS, which is brilliant, and you probably haven't heard of it. I feel like an SFS hipster, by the way. The web. So finally, it's kind of taking all these things and saying, let's upgrade the web with this cool thing. So yeah, so you can mostly BitTorrent and Git on the web. That's kind of what you've heard about. So there's this like timeline, right? In the 90s, the web came out, and there was this massive explosion where like everyone was like, files and documents and links, and I can access everything in the browser, and I can see it all, and the world was good. That was pretty cool. And then there was this other explosion around 2000 where it was like peer-to-peer and like big files and like sharing, and by the way, most of these things were illegal at the time. But things like Skype came out, which was this entire VoIP system riding on peer-to-peer. Like this entire massive industry or company servicing hundreds of millions of calls entirely in peer-to-peer, right? Like, how did that happen? In reality, they had a pretty sophisticated infrastructure where they ran many servers too, but they were able to connect all these people really seamlessly, and that was amazing. Like, how could we take those ideas and say, let's, again, upgrade the infrastructure of the internet to just support that from the get-go, rather than having to build like, this large application around it. So then Git and Bitcoin came out, and both of these, Git was around 2005 and Bitcoin 2008. Both of these things, very different, but they use the same data structure, what I'm calling a merkle DAG. You probably have never heard that term because I coined it, and a friend of mine helped me think through like just how amazing this data structure is. I opened my eyes up to like understanding that this data structure is really what it's all about. So you probably have heard of Git as a merkle tree, but in reality a merkle tree is something slightly different. So we really need a better term, and that's why I'm calling it a merkle DAG. All it means is, yeah.
What is a merkle tree?
Ah, cool. So a merkle tree just says, take this really big file and slice it up into a bunch of chunks. And for each of these chunks, you're going to create one hash. And now you're going to assemble these hashes into a tree, into a binary tree, where you take these two hashes and you create another node that's a hash of these two. You take the next two and that's another node, and so on. All the way so you have this really big binary tree. And it allows you to really quickly see like a path of changes, right? If I change any one of these blocks and I generate another merkle tree, I can just ship you the merkle tree, which is very small, and you can see what has changed. The original applications were around like cryptography, really cool, like awesome stories, so like go look at it. But the people basically said, this is a cool idea. What if we use something like a merkle tree, but not quite a merkle tree, and said, we have some object of data, and when it points to another object, let's embed its hash, the hash of this object, which is really addressed, right, into the object. Kind of like the web, right? In the web, you have a file and a document, and it points to another object, and you embed a link. But that pointer is not really permanent, right? It's that pointer says, get this object somehow, and it doesn't even tell you what object that is. I could serve you a totally different file. That's not. These two new tools you're going to start hearing a lot about. DAT and IPFS. So this is totally biased. I'm actually working on both of these, so bear with me. DAT is kind of like trying to take the lessons of Git and apply them to data. and creating a whole bunch of amazing workflows around how people deal with data. So think of all the magical ways that people assemble repositories and share them and have all that kind of stuff. Like that's what that is really about. And that's where like my dataset package management efforts have like now gone to. And then IPFS is this like more low-level thing where it's really about just files and blocks, and you don't really care about data. You don't really just care about addressing things between them and just supporting this merkle DAG. So you can actually build that on top of IPFS. And you can also build Git on top of. All right, we'll get to this. The last thing I'm going to mention is that during this timeline, all these amazing ideas came out, right? So in the last 25 years, which is basically my lifetime, we've seen the web, we've seen all these peer-to-peer stuff emerge, like that's Kademlia, that's BitTorrent, that's the Git merkle DAG data structure, that's Bitcoin, like all these amazing stuff is happening. And it's not actually crazy to come up with the idea to say, hey, I have this new thing, let's build it into the infrastructure of the web, because, you know, like, the timeline is very short. You know, in 10 years, like we'll look back to today as yesterday. Stuff moves really fast. And the other thing is, these changes came in waves, right? At the very beginning, when the web came in, it made this explosion of everyone connected to the web. Then peer-to-peer caused another explosion. Then I would argue that like, we went away from peer-to-peer because most people migrated to using services through mobile. And peer-to-peer and mobile kind of sucks, right? Because you don't want to connect these devices that are behind like many layers of apps to each other. But that's getting better thanks to WebRTC. So I predict there will be a lot more peer-to-peer stuff coming for mobile. And so what will be the future? I argue it's about data. It's about linking data together in the same way that we link the web together. So link data, right? Like the semantic web, that's old news, like we all know about it. But I really think that that's coming, but what will get us there is better protocols that are high performance, right? Like the semantic web world doesn't really claim to give you really high performance, and that I think is the key. All right, so that's kind of the background. Quick overview. So I think the best way to explain IPFS is to just go through the stack. It's a stack of different ideas that have been synthesized, right? So I'm trying to take ideas, good ideas that came in all of these technologies, and say how do they fit together to create like the next thing in this series of good ideas. And by the way, like most of this stuff was really like, it's not really my ideas in the sense that these good ideas existed, and it was just me observing them and realizing how good they fit together and synthesizing them in an interface that makes sense. So the stack. At the bottom there's the network, and you can look at any kind of network that you can connect to. So you can think of this as like UTP or WebRTC or anything that will just give you some reliable channel. It doesn't have to be TCP. It could be anything. And making that choice very specifically because I want to be able to run IPFS nodes in a web browser. So like inside a web page. Just drop some JavaScript in there, and that's a full IPFS node that can access files. This thing needs to be able to be as flexible as HTTP. Like that's what made HTTP amazing. It was just, you can use it anywhere, and you can get any files. That's what we need. But it needs to be better. So routing. Routing is really about how you get files. Like how do you find out who has a specific file? We have good ideas for how to do this. There are DHCs. People have come up with these. Kademlia is probably the most famous one that you've heard of. And but you can use any kind of routing system that responds to some API. Then there's this exchange part. That's where BitTorrent comes in. So yeah, I'll explain it more in a second. The merkle DAG is on top of that. Then we have naming, where mutability comes in, and files on top. So I have mutability here at the last part because as I started working on this, I realized that all these great systems like Git or Plan9 made this very strong distinction between mutable and immutable content. And that by making the distinction, you could optimize a lot of how you arrange files that you know are immutable, because you know you can cache them forever. Right? And so if you make that distinction clear, all of these systems get easier to implement. And you layer mutability, you sprinkle it at the top by just changing pointers. Think of Git, right? Like you have some code, you have some existing version control tree, you make some changes, and you're going to go commit them. When you commit them, you've now changed some files, which means new blobs are going to be created. But you're not actually changing any of the old files, you're just adding, you're just writing more. right? This is what makes Git have this distributed version control amazingness, right? Because you can just keep adding, and other people can keep adding, and the only conflicts really come when you're when you're restructuring the tree and seeing what mutable changes you've made. Cool. So hopefully, I haven't lost everyone so far. Kind of dancing it up into a lot of things. All right. So routing. Yeah. So it's pretty simple. You just basically want the ability to just put a value into a system, and then get it back out with a key, right? It's just a hash table. So that's what a DHT means. It's a distributed hash table. And this is really necessary because you want to be able to find who has the value, right? When you get a HTTP works by putting the address into the URL, because that just tells you where you need to go to get the file. But if you remove that constraint, you now need a way to fix that, and that's what DHTs are for. The IPFS DHT is a little bit different because it also has this put peer or get peer thing. So people realize that if you want to host really large things on DHTs, it's better if you add a layer of indirection of saying, here's all the people that have this value, and you list them in the DHT, and then later you can go and get them. So if people have used BitTorrent in the last 5 years, you've probably seen this magnetized link transfer thing, right? This magnetized URL. What that means is that it's giving you a hash, and you're now going to open your BitTorrent client, you're going to connect to a peer node, to the DHT, and you're going to say, hey, does anyone have this hash? And you're going to get back a list of peers. You're going to ask them for the torrent file, they're going to give it to you, and now you can bootstrap the BitTorrent part. That's kind of how it works. It's just a DHT. So the same thing here. The exchange is where it gets interesting, right? So the amazing thing about BitTorrent was this realization that instead of requesting files directly from one node, if the server that's serving out a file is a little bit smart about how it's giving out the file, then you can get great bandwidth utilization, right? If all of you were trying to get a file from me, and I just started to try to sequentially give it to all of you, I'm going to be overwhelmed. But if I understand that you are all trying to get this file, and I give you a small piece, and you a different small piece, now you two can go and trade, right? You can send him the piece that he doesn't have, and vice versa. This idea is just pretty simple, but it's brilliant. And you couple that with this tit for tat mechanic of saying, I'm not going to give you anything unless you give me something. And you get a market, right? And markets are good at optimizing systems. And so you get this massive explosion of bits, right? Just people are sending data really, really quickly, right? And so even today, it's amazing how for peer-to-peer traffic, for really large things, BitTorrent is still today the fastest thing around. And if you're going to host really large files, you do it through BitTorrent because it's just much easier, right? Your server's not going to fall apart. Unless, of course, you can pay for massive amounts of servers, but not everyone can. So I like this graph. This is from academictorrents.com. It's a really cool site, which hosts a bunch of torrents important for academia, like data sets and so on. And this just kind of says it all, right? It's here, I don't know if you can see it, but there's HTTP is going down, right? As the number of peers increases, the download speed for everyone is just increasingly going down because this sender is getting completely their bandwidth is getting completely destroyed. Whereas instead, in BitTorrent, you increase the total download speed for everyone as the number of peers increases because the distribution of data is better across the whole network. So that's pretty awesome. Let's take this idea and sync it into the infrastructure of the internet. It's awesome. BitTorrent should be running the world, I would argue. So it kind of looks like this. You probably have seen diagrams like this, and so on. And it really turns into a market. So the problem when putting BitTorrent into IPFS is that BitTorrent makes a bunch of assumptions about how the files get structured, and you have this mutable thing. So I had to generalize the protocol to be able to handle lots of different objects that are not known a priori, right? BitTorrent works by, we know exactly what we want, so we can trade really efficiently. In BitSwap, you don't have that prior knowledge, so you have to, so it turns it into kind of like an auction of saying, hey, I'm looking for these things, and if you have them, then you can contribute to me. And if you contribute to me, then our standing has increased, which means that I'm much more likely to give back to you in the future. So this is a whole talk, but yeah, so basically you just get this notion of saying, magical network that gives you a block from a key, and it works by BitTorrent assumption. Cool, so that's the exchange. on top of that, now that we've built like this really fast way of getting blocks, what if we traded merkle DAG objects, right? Like what if we put your Git log store on top of this thing? So what does that mean? So Git has this, again, awesome, cool workflow, and it has this merkle DAG data structure. So here's where you can see it, right? So if you look at the version 1 file up at the bottom right, we have this blob. This is how Git works. You create this file, you give it a hash, then you take that hash and you put it inside the tree in that pointer with a name. So the tree has the name test.text inside of it, and it has the hash, and that's how the pointer works. This diagram is not very good because it should show that the hash is in there, so I'll make that better in the future. And then you have a commit, right? And when you make another commit, and you change that version 1 to version 2, you create a new object, you create a new tree that now also has another file, and you create another commit, and so on, right? And all of these objects are part of your data store, right? Like you're just increasing the number of objects because they're all immutable, and that's the magic of Git. So let's just do this for everything. Like let's take all the data and structure it this way. But we're gonna have to make some changes. Like, first of all, this tree blob abstraction, maybe we don't need it. Maybe we don't need to think of directories as trees. Maybe in reality what all of this means is just that you want some object to be able to hold data, and you want objects to be able to point to other objects, right? So kind of like HTTP. You have some data, and you have some links. So let's just do that. Let's just say in the IPFS merkle DAG, you just have objects that have some opaque data that IPFS doesn't care about, and they're able to have this extra link structure that IPFS does understand to be able to point to other things. And this basically gives you path resolution, right? This is like where the magic comes from the merkle DAG. You have, /IPFS/ you put in the hash of an object, and then after that you can create a path. So don't pay attention to that disgusting looking hash in there. We're going to get to that in a minute. But you get like /IPFS/ some big hash, and now you can resolve paths underneath that, right? You can go like food bar bass, like all the way. And each one of those objects is accessible through its own hash too, but this is how you get URLs, right? Or like the equivalent of URLs. Any questions so far? Yeah.
So if I have a Git repo, I generally like clone the whole repo.
Yeah.
If I have information about everything, I probably can't put the whole internet or the whole web on my laptop, right? So like how do I subset this?
Yeah. So the idea is just you have some hash,
Okay.
and you say I want to get the object that this hash points to, right? And you ask the exchange system, give me the block this points to. You pull out that block, and then that one has links to other things, right? So you can just recursively go through and get that subsection.
So my hard drive is like a cache that can be garbage collected?
Yeah, exactly. And if you want things to really stick around, then you can just pin them. And we have this notion of pinning an object, and you can pin recursively, right? So if you have your Git repository, which is really just a sub. Think about everyone has Git repositories, right? And they're all a different tree. Why do we have different trees? Why aren't they all part of the same massive tree? It's because it's complicated to think about commits and different commit hierarchies. But it's also complicated to think about submarkets, and that never got, really fixed. So, yeah.
Related to that, say you don't know, a hash can't live in just one location. It has to live in multiple locations, because what if, computers are down, right? So as this network is so small, how do you build out a model for how you decide to distribute the content?
That is an excellent question. I'm going to defer. So I'm going to defer this to the end.
Okay.
First of all, the very basic idea is that IPFS says that whoever just has the data because they care about it locally, then can serve it, right? Maybe not everyone will because you don't in the exchange system you don't really need to, but yeah. So you have a bunch of objects, you can pin them, and you can now serve those objects that you pin. But the other question of how do you incentivize the whole world to store these objects? It's a very interesting thing that we'll talk about.
So is this primarily just going to be for the static web?
So the difference between dynamic content and static content is just how you use it, right? So Git is static, but in reality it's not, right? You can mutate things, just that you write more. So think about a stream of data. Think about a video stream, right? So if I'm taking a large TV stream, so I'm receiving this stuff, nothing prevents me from just picking some chunk size and saying, at this chunk, I'm going to put this into the file. I mean, at the end of the day, you have to break it up into packets, right? So you always have some fixed size chunk that you're sending things through. So you can now structure these objects this way. It's probably not going to be as fast as you want it to be for video streaming because you want really low latency, but it's going to be very good for like just storing the stream later.
But what about like application logic?
Right. So this is for distribution of data. Right. So HTTP today, even though it's this document exchange system, has now become two things: data distribution and logic distribution, right? Like exposing APIs. So I think HTTP is really good for exposing APIs, right? All this like endpoint and REST and all of these amazing, all the methods that you get and so on are really good for logic. You can just return references to objects in IPFS. That's kind of like the feature that I see. You can use HTTP for logic and IPFS for data.
So like I have a large file that I want people to download, or I'm streaming the video from the site.
Yeah, or
like all static assets, basically, right?
yeah, exactly. Right. So people are already doing that today. Like they're using CDNs, right? If you're going to serve a lot of files, you're not going to serve them from your HTTP server. You're going to serve it through a CDN. It's the same idea.
So, how do you think about deciding whether to have IPFS like as a CDN versus a file system, at least initially, right? Because you could have like IPFS : / right? Like as a versus like a full-blown file system, which seems like harder.
Yeah. So I have IPFS.io, which will resolve any object you get, and it will be running a node that will just serve IPFS objects. You won't store any of them, but just serve them. That's going to get, like, as people start putting these links into their pages, then you can start doing things like adding either browser extensions or just JavaScript directly into the page. That's going to be smart and say, this link to http://ipfs.io is really an IPFS link, so I can fetch it. I don't have to request that server. But that's getting into like how do we take this idea and then like make it make sense for the world today.
Just to be a little bit more clear specific. So if this is going to be serving static assets, I guess my question is, how do you decide whether to sort of view it as like a CDN versus as a file system which has like a different API?
It's a good question. Like this thing is so general that like, is it a CDN? Is it a file system? Those are two different use cases, right? Is HTTP a CDN? Is it logic? It's just a protocol, and it gives you different properties. You use it, right?
BitTorrent, right? Like we use it for downloading any kind of file, but the company itself, I don't know if you guys know this, but it's primarily a CDN. Right? Like the business use case is a CDN. The user-consumer use case is just distributing all kinds of files.
Yeah.
So just like a quick comment, you can't do it in JavaScript. It would have to be on the browser level because what most modern web browsers do is they prefetch as they stream HTML. So you'd have to change like any SRC attributes like data SRC.
Yeah, exactly. So to that, I refer to my friend Faraz. So I don't know if you know about him, but Faraz, a good DJ, had a pretty similar idea around building a pure CDN on the browser that uses BitTorrent, like straight up BitTorrent, or something like it. I think it was a slightly different protocol. It's really cool. Like, he got this working. Like he got this working to the point where you have this JavaScript file, you dump into your page. As you're requesting, it changes the link structure to then query the peers. It's really, really cool. So it still works. You should go see it. So same idea. Just that's how IPFS is going to work. It's going to use the same kind of trick. But ultimately, I really want browsers to just support this later, right? And if it becomes useful enough to people, then that's easy. It's just a matter of sending patches. Cool. Any other thoughts? Yeah.
So right data from Google for these files will come with the computer. So if I change the file a little bit, it's just encrypted.
Yeah. So what happens with encryption, right? Well, you can do different things, right? So you can encrypt a file, and then nobody else can distribute your own keys. And either you share the keys with somebody else so that they can see it, or you can encrypt files along the way, right? So if I have an object over here that points all the way down to some resource, I can encrypt this object, and you not necessarily the other one. So that when you change it, yeah, let's probably defer that to offline because that's a complicated case. But there's a way to handle this. Yeah, let me just go through and then tell you how we get mutability. By the way, this is David Nazaris. This picture is like from his website. He's one of the smartest computer scientists around, period. So Gwen and I both worked with him, and he is pretty brilliant. He came up with Kademlia, came up with SFS, a whole bunch of things. So if you ever want to find out about new ideas that you've never heard about before, just go to his papers page and just randomly pick. You're guaranteed to find really good ideas. And if you don't think they are, you probably don't understand them yet. So thank you, David. It was awesome. Anyway, so naming. I said we're going to get rid of this ugly hash, right? So this is a trick from David, and it's called SFS. It was just PhD thesis. The idea is, if you're posting some research on the web, and I'm giving people a path of some sort, let's go away from the content address thing for a moment. That's why there's a different prefix there. It's IPNS instead of IPFS. And just say this is a mutable URL. And instead of being this content address thing, I'm going to take the hash of the public key, and I'm going to request it on DHT. And what I'm going to get back is not going to be the public key as I expect, normally with IPFS, but instead, I'm going to get an object that is really just a hash to something else that's signed by that public key. So what you get is this mutable namespace that only I can write to, because only I can sign that object with my private key, right? Sorry, that's a signed by public key, but I really should be signed by private key. Does that kind of make sense? Let's think it for a moment. You have a namespace, a completely global namespace, where we can all write to simultaneously, and write to different paths, and we can get mutability by using the hash of your public key as a way to address it. It's really awesome. So with that, and this really cool trick of just saying, if you really want nice looking names, you can use DNS. You put it on a text record, you get mutability, right? So now I can host something on IPNS/hash of my public key and put some specific object that I want you to look at, take the hash of my public key, put it on a DNS text record, and now you can resolve this nice looking path, right? And that's a mutable path. So I can then go and update foo.txt later, and you can get the updated version.
And then you need the public key to check that.
Yeah, so you fetch it from IPFS, right? IPFS/hash of public key. That will give you the real public key.
So this bootstraps by putting records on the DNS.
So you can. I really don't like DNS. It's really awful, but it exists and we use it. So for now, let's just use it because people expect it. You can then do later other crazy things like start resolving other namespaces, right? Like saying IPNS/whatever.bit, which is like the Namecoin namespace, or .onion, or whatever. And more importantly, later you can just mount IPNS/some big hash as your namespace, or your name service, and you can resolve names under that. That was another contribution from the SFS paper. It just said you can make distributed namespaces. You don't really have to have the centralized authority that hands out the authority of naming. You can anyone can set up a namespace and say whatever they want. You just need to be able to get them at the beginning. So it's kind of like how DNS works anyway, right? We all have this baked-in IP addresses for DNS in our systems. It's a similar idea. So that's kind of the IPFS stack. There's a lot here. There's a lot of ideas. I probably have gone way over more than time. But that's kind of the background that how all of these things mesh together, right? So you can see BitTorrent, you can see DHTs, you can see SFS and Git all coming together in this nice interface. I probably haven't done the best job at explaining it, but there's a paper that you can read that I wrote and put out there, and you can read it, and hopefully that will explain it better than I am today. It's kind of sad when I say, go read the paper. I'm not good enough to, I'm not as good as the paper. All right, so some really quick use cases. I just want to run through these really quickly, and I'm not going to spend time on them, just kind of mention them, right? So as a mounted global system, global file system, you could have all of IPFS mounted under /IPFS and /IPNS. So you could request any object and open it, and IPFS would just go fetch it and stream it to you. You could have a personal sync folder that's kind of like Dropbox, that when you drop a file into it, it automatically versions it and adds it under your namespace in IPFS. Right? So you can just use it like Dropbox, just add stuff, and it'll appear elsewhere. But the syncing is happening through IPFS. And files that are shared between people are deduplicated, right? So you can crypt files. I said I wouldn't talk very much about crypto at the moment. You can mount package managers into your system, right? So today we have this notion that package managers, we like make requests and download things and then they're installed. But what if they were already installed? What if we had like /apt in your file system, right? And just everything was already there, so that when you access it for the first time, it has to go fetch it. It's kind of a crazy idea, but it could work. So you can use it as a root file system on a virtual machine, right? You could boot machines entirely with this as the file system. Moreover, you can have a hypervisor and say, hey hypervisor, here's a hash, boot this machine. And that points to not just a VM image, but just like the hierarchy of what the file system should look like. So the entire structure. You can just, the hypervisor would be like, great, let's set up that system and go. And you can log into it, make some changes, and as you make changes, they get committed into different objects, and you now have a different hash. So you can always be sure what your system is pointing to. Kind of like today when you can say, my code base is legit because I know what hash it should be at, and I know that that's correct. What if you could do that for the entire system, right? I am at this hash, and you can say like that's what our VM looks like. That's what our production service looks like. Docker, by the way, does similar things. Pretty awesome. So things will go hand in hand really well. You can even use it as a database to just start writing arbitrary data structures in the merkle DAG format and just throw them into IPFS. It doesn't have to be a file. It could be anything. That was a kind of cool realization that came down the road. And you can use it as a CDN, right? You can just distribute really large files, use the magic of peer-to-peer, use the magic of like just really fast distribution, and you get that out of the bag by just using this. So, and in the end, I want to get to a point where we have a web and we have links in there. And I can, at the time of fetching, back up every object that that link points to and have it forever. So that in the future, if I go to look at that page again, I don't have to find a 404, right? If that website is dead for whatever reason. That's really tragic and we should go away from that. We need to start backing up the important files in the world. And that's how IPFS can get us closer to the permanent web. It's not quite permanent yet, because IPFS does not incentivize you to store everything you want. But stay tuned. All right, so the future of IPFS. It's early. I've spent the last few months writing the protocol and designing it. It's up there. It's on a Git repository under /kbanet/IPFS. You can go to it. This is a protocol. Different implementations live. There's two implementations right now. There's a Go one and a Node one, and I'm kind of doing both of them concurrently. So I'll probably finish the Go one first. And so, yeah, like that's kind of how everything's on through GitHub, everything's open source. Everything is MIT licensed, so you can take this and do whatever you want with it. So no GPL. So here's some links for you. Here's the website, the paper, the protocol, the Go implementation, the Node implementation. That's me, GitHub, and Twitter. You should, I don't know, stay in touch. If you have any questions or comments or anything, please reach out. There's a lot in this talk, and I kind of want it to be really high level, but we can sink deeper in later conversations. And hopefully someday, those links will turn into this. So maybe at some point, we'll see that. And this is what the website will look like, or something like this. It'll probably have more images and videos, because that's what people want. And thank you, Sourcegraph. Thank you very much. This has been like super awesome. Thank you for having me here. And it also forced me to get all of these ideas into a more digestible format, like a conversation. Although I probably lost half of you, like most of the faces, so I'm sorry. But hopefully this was interesting. Hopefully this gave you a different perspective, and at least made you interested enough to go check out the source of the protocol. And soon, this will be implemented. And so just for this room, so don't publish it yet. Well, this is going to go on a video.
Yeah, I was just going to take it over.
Yeah, but is it going to be posted tonight or tomorrow?
And I'll just,
Yeah.
yeah,
Well,
edit.
it's fine to leave it in if it goes up to like tomorrow or the next day. Actually, it's probably fine. But it's okay. So, this thing called FilePoint is how we incentivize people to store files everywhere in the web. I took BitTorrent and modified the work function to force people to prove they hold certain files. And that's how they mine. So they mine by proving they have certain files. And that's how we incentivize just like seeders for all of the content around the world. This is crazy too. And there's a paper that you can go look at as well. I should show you the IPFS paper too. So you see it's real. There it is. Big paper. Cool. So thank you very much, and thanks for having me.